linear induction motor, linear synchronous motor, linear DC motor, linear reluctance motor, linear levitation motors, so on. So we will see. The outline of the presentation is nothing but the introductory part, the construction, the principle of operation, then how the linear induction motor works, the linear synchronous motor works, linear reluctance motor, advantages, disadvantages, application. So moving on to the linear induction motor part. The linear induction motor means that is nothing but it has to convert the electrical energy to mechanical energy. The only difference is that is having a translational motion or a linear motion or a rectilinear motion rather than having a rotational motion, as in the case of conventional induction motor. So the linear electric motors, as I have already told, this can be classified as linear induction motors, linear synchronous motors, linear reluctance motor, linear DC motors. All are having, the only difference is from the conventional type means the linear counterpart of conventional induction motor is a linear induction motor. Linear counterpart of a rotating DC motor is nothing but a linear DC motor. So we will be moving on to the linear induction motor first. So in the linear induction motor means here you will be having a straight line or a linear motion rather than having a rotational motion. And when you are considering a conventional induction motor, that will be having a stator and a rotor. As you know, stator is a stationary part and the rotor is a rotating part. And the rotor always spins inside the stator. So that means a rotating magnetic field will be developed there. When you are giving the three-phase supply to the stator, what will happen is a rotating magnetic field with synchronous speed will be developed there. That rotating magnetic field, according to Faraday's laws of electromagnetic induction and induced EMF, will be developed in the rotor. And this rotor, since it is a closed circuit and induced current will be flowing through that one, and that will develop a torque and then it will be rotating. That is a rotational type motion. But in the case of linear motor, how you are getting a linear motor state race, that is nothing but you have to take a conventional motor and you have to cut it and then you have to stretch it. So that means you are getting it as a unwrapped and laid out flat one or a open type. Okay, you have to stretch it. So you will get a straight line motion. So it is nothing but an advanced version of a rotary induction motor and which gives a linear motion instead of a rotational motion. So you can see you are having a three-phase winding, then you are having a stator, then you are having a rotor, and you are having an aluminum sheet or conductor is there. Then you can see an AB part will be there. If you are cutting that AB section axially and then you are stretching it and you will get the primary of the linear induction motor. So that means if the stator is cut along the line AB and spread out flat, giving a primary of the system. This primary of the system is nothing but you can call it as the field system. So this field system, you can have either the single primary or you can have a double primary system. So here you are having a three-phase winding and you will be having a primary. This will be acting as the primary, that is the field system. And this primary system consists of slots and the slots carries the three-phase windings. So the three-phase distributed windings will be inside the slot and that forms the primary, that is the field system. And you can see here you are having an aluminum conductor is there, then you can have a secondary is there. So here the stator and the rotor, here in this part you are calling it as the primary and secondary. In the conventional case it is a stator and rotor, but in this case it is a primary and secondary. So this is when you are cutting the induction motor axially and spread out flat, you will get the primary, and the primary is nothing but the field system. And the field system carries the three-phase distributed winding and it produces the magnetic field, and it can be a single or a double primary system. And the rotor is nothing but an aluminum or a copper conductor, and that is having a ferromagnetic core is also there to reduce the, that is to increase the effective flux linkage. So this is the section, that means the conventional section, you have to cut it, you will get the primary, and this is the cross-sectional view. Here also you can see the each part, the rotor, the secondary, the stator, the primary, the slots are embedded in the slots are there, and here the windings are provided, and this is a linear motion. And this, when you are cutting, you are getting the primary, the same as that of the previous one, which is the similar view. So you are having a three-phase squirrel gauge induction motor, you have to make a cut and then open out flat, then you will get a three-phase linear induction motor, that is a smooth rotor will be there. So here you can see the coils, the rotor and the stator part. Okay. And the secondary means you are having a construction sheet and you are having a reaction plate will be there, that's the secondary. So the linear induction motor, since it is having a larger air gap, normally in the case of induction motor, you are having normally the 2 mm air gap thickness will be there. But in the case of linear induction motor, you are having 5 centimeter air gap will be there for the traction purposes. So since it is having a larger air gap, means you will be having a large magnetizing current will be there, that will automatically reduce the power factor and efficiency of the motor. So here, in the case of conventional, you are having the stator and the rotor area remains the same. But in the case of the linear induction motor, it can be either the primary or the secondary can be shorter one or a longer one. That depends upon the application. So at the if the shorter part will be passing continuous, since the at steady speed, what will happen is the shorter part, if you are having a shorter primary and a longer secondary, then if the shorter part will be a moving one, then that will be continuously moving around the rotor part. Okay. So the linear induction motor can be classified as axial field and transverse field motors. So we will see what is axial flux linear motor and transverse flux linear motor. Axial flux means it will be mainly used for medium and low speed application, and this will be mainly derived from the conventional squirrel cage induction motor. As you can see, it has a primary and the secondary. Either the primary or the secondary can be a moving part depending upon the application of linear induction motor. When you are moving to the transverse flux linear induction motor, the secondary is provided with a steel backing. Why we are providing a steel backing? As you can see in the secondary, normally here you are having a steel backing, but in the case of axial type, it is not there. Why we are providing the steel backing is usually to reduce the reluctance of the magnetic circuit. And this is mainly used for high speed application, but the axial type is mainly used for low and medium speed application. And here in the transverse type, no restriction on the pole pitch, since you are not conveying any flux in the axial direction. It has single slot per pole per phase. And the most important thing is the successive core must be separated by a minimum distance to avoid the axial thrust. Then only you will get the full utilization. And you are having a double-sided primary is also there. So in the double-sided linear induction motor has a primary on both sides. As you can see, in both sides the primaries are there. So far we have seen only one primary and secondary will be there. But here you can see both the sides you are having primary and you are having a secondary is also there. So that is known as the double-sided primary sector. Here this can see the single linear induction motor, that means a single primary is there. In the double linear induction motor, you are having a double primary system is there. So when you are moving to the principle of operation, the linear induction motor means the conventional induction motor, when you are giving the three-phase supply, then you will be getting a rotating magnetic field will be there, and that will create a flux, but that will create a torque. But in the case of linear induction motor, the primary of the linear induction motor, when it is get excited by a balanced three-phase supply, instead of a rotating magnetic field, you are getting it as a traveling flux wave that is produced, which is travel along the length of the primary. So a current will be induced in the secondary conductor since it is an aluminum material due to the relative motion between the traveling flux and the conductor. And since you are having a current induced in, that means that will interact with the traveling flux magnetic field and it will produce a linear force, or we can call it as the linear force, or we can call it as the propulsive force, or you can call that as the thrust axially. So this force, when you are in the case of conventional induction motor, you are having torque, but instead of that one, you are having a force in linear induction motor. And remember, this traveling flux, the secondary current and the force are mutually perpendicular to each other. If the secondary of the induction motor is fixed and the primary is free to move, means the force will move the primary in the direction of the traveling wave, resulting in a rectilinear or a linear motion. As you can see, this is the flux density, this is the current and the force, they are mutually perpendicular to each other. And this is the classification. Classification means you can have the linear induction motor, short primary, short secondary, double primary, coreless type, composite secondary, sheet secondary is there, flat and tubular type is there, transverse longitudinal is there, surface primary winding, gram primary winding. Different types are there, single entity is there, double entity is there. So you can have the different classification areas of linear induction motor. We will see some of them. So in the linear induction motor configuration, mainly you have to study the three types. That is the short primary, the short secondary, the double primary. So we will see the short primary. Short primary is nothing but, as you can see, the primary to the magnetic or to improve the performance of the magnetic flux path. So here you are having a primary and the secondary will be there. So the primary is short. So where here you have to use, since you are having a short primary, means that has to be used when the distance traveled is more. So here you can see when the distance traveled is more, you have to apply this short primary type. And remember, one more thing is there, the overheating of the rotor can be eliminated. Why? Because the movement of the primary over the cold part of the rotor when leaving behind the heated part. So that means the overheating of the rotor can be eliminated in the case of short primary. And the case of short secondary means, as you can see here, the secondary is short and the primary is large. And this is the ferromagnetic plate. And the secondary is short means this is useful when the distance traveled is limited or it is a lightweight one. And what is the drawback of this long primary and short secondary? So if long primary means, as you know, the long primary, you are having the three-phase distributed windings will be there that is accommodated in the slot. So that is uneconomical since it requires a long three-phase windings to be wound. So and again, one more thing is there, the part of the primary winding which are adjacent to secondary are effective at any time. So that is also a drawback when you are comparing that primary type. So depending upon the requirement of either the member can be a stator or can be a rotor. So the use of the motor decides which which of the two, that is the primary or the secondary, is a shorter length compared to the other. The primary is made shorter than the secondary, as we know, when the distance is large, and the secondary is made larger when the distance is limited. And the single primary system drawback means, in a single primary system, the ferromagnet plate is usually placed on the other side of the conducting plate, right? So you will get a low reluctance path to maintain the flux. Then the ferromagnetic path plate will get attracted towards the primary when the field is energized also. Consequently, as you know, obviously unequal gap length will be, air gap length will be resulting and on the two sides of the plate. So this can be avoided by using a double primary system. So in the double primary system, you are having a primary and you are having secondary, and you are having that means two primary sides are there on either side of the secondary part. It minimizes the leakage flux and avoids the magnetic interaction between the moving parts and the reaction rail, that is the secondary. And this is the different types, that is nothing but short primary, and this is the short secondary, and this one is the coreless sheet secondary, that means no core will be there. And then you are having a double primary, two primaries can be added. So tubular linear motors are also there. So in tubular linear motor means that is nothing but it is a conventional induction motor. You have to cut it axially and re-rolling along the lengthwise direction, you will get a tubular type. So this tubular type. And here the magnetic field is produced within the tube when the primary winding is energized with a three-phase supply. And next we will see the forces in the linear induction motor. You are having normal force, lateral force and thrust force will be there. All are perpendicular to each other. First we will see the normal force. The normal force means if the double linear induction motor plate is centrally located between the two primary stators. If you are having a two primary stator and a reaction plate and it is centrally located, and the force between the stator and the reaction plate is, one stator and the reaction plate is not equal to the force between the stator and the reaction plate of the other. That means it is equal and opposite. So that means the normal force will get cancelled and it will be equal to 0. And the normal force will occur if the reaction plate is placed asymmetric between the two. Then the force will tend to center the reaction plate also. It will be always proportional to the displacement. So as we can see, this force shows the asymmetry of the system. And when you are considering a single linear induction motor, there is a large net normal force will be there because it is not a double primary, it is a single primary one. So there will be a normal force experienced between the primary and the reaction plate. So the attractive force will be there, and sometimes you will be having a repulsive force will be there. So we will see the attractive force and the repulsive force. So you can see here is the repulsion when you are considering the synchronous speed, and as the frequency is increasing, you will be see this is the attractive force and this is the repulsive force that is corresponding to the normal force, that is the variation of force with the speed and frequency of the primary current. When you are considering the normal force, you can see the repulsion force, that means the normal force will be in repulsive manner, and you can have, this is the attraction between the normal force. So this is the resultant force will be the attraction normal force minus the repulsion normal force. Suppose if it is the force is there, that will try to align it into the center part. The reaction plate has to be centralized. That is the secondary one. So next we will see the thrust force. That is the force responsible for the useful work. So then you are having another force, that is the cogging force, that is mainly in the no load condition, where the force of attraction between the core and the primary and the magnet is termed as the cogging force at no load condition. Detent force is mainly associated with the permanent magnet, that is attractive force component will be there, that is maintain the alignment between the stator teeth and the reaction plate with PMS, permanent magnet machines. And we will see lateral force, and these forces are acted perpendicular to the daughter position, that is the y direction. These forces make the system unstable greater than 60 degrees, 60 hertz. And due to asymmetric positioning of the stator and induction motor, any displacement from the central position will result unstable system. So at high frequency operation, the lateral force can be quite chaotic also. So here in the lateral force, mainly you will be having an ejection type lateral force and a realigned primary force will be there. The resultant lateral force may be either decentralizing or centralizing primary. As you can see, you are having a ejection lateral force will be there, that is in this direction, and you are having a realigning lateral force will be there, that will always center the primary system. The resultant will be the difference of the two. And next we will move on to the working principle. The working principle means when the three-phase primary winding of the motor is energized from a balanced three-phase supply, a traveling flux wave will be produced, which will be having a magnetic field with linear synchronous speed Bs rotating with, linearly varying with the linear synchronous speed Bs. And the linear synchronous speed Bs can be written as 2 tau f. But in the case of conventional motors, we can written this n as the synchronous speed as 120 f by p. Here tau is nothing but the linear pole pitch. And here, as in the case of a conventional induction motor also, you are having a relative speed of the stator and the rotor will be there. In the conventional, NR will be equal to 1 minus S into NS, that is a rotary type motion. Here you are having VR will be equal to 1 minus S into VS. And the slip in the case of conventional type, you are getting it as NS minus N divided by NS. Here you are having S is equal to Vs minus Vr divided by Vs. And here you will be having the air gap power and the mechanical power developed will be the same as that of the conventional induction motor, that is 3I2 square R2 by S and 1 minus S Pg. And how will you get the thrust equation? The thrust equation is nothing but you have to obtain the relation from the power developed. So the gross power developed will be equal to 3 into E1 I1 cos phi. And as you know, the EMF of the induced EMF in the primary, as that is nothing but 4.44 F kW T phase into pi m, where F is the frequency, kW is the winding factor, and the T phase is the turns per phase, and flux is the phi m is the flux per pole. And this is the then you are having two important parameters for the design, that is the specific electric loading and the specific magnetic loading. Specific electric loading means that is nothing but that is equal to the total armature ampere conductors divided by the armature periphery of the air gap, or you are getting it as equal to 3 into the conductors is 2 into turns per phase into I1 divided by the length of the primary. From that you will get the current I1, and the L is nothing but P into tau. And you can get the specific magnetic loading, that is nothing but the total flux around the air gap divided by the area of the flux path. So that will be equal to V average will be equal to P phi m divided by area, that is L into W. So you will get phi m also. So when you are substituting these values in the power equation, you will E1 and I1, you will get the developed power, that is equal to, instead of E1 you can substitute here, instead of that is I1 is like that, instead of E1 you can substitute here, and here you have to substitute in the E1 expression, you are having a phi m, so phi m can be substituted from the specific magnetic loading, and I1 can be substituted from the specific electric loading, and then you are rearranging the expression, you will get this expression, that is known as the gross power developed in the motor. And the thrust developed will be equal to, that is equal to efficiency into this air power divided by Ps, and or you can have this efficiency into the mechanical power developed divided by the rotor speed. So then you will be obtaining the thrust developed will be equal to this one. Rearrange the expression to get 1.11 into this one will be the thrust developed, and the copper loss will be S times slip times the power developed, and mechanical power will be equal to the same as 1 minus S into Pg. The thrust velocity curve is nothing but you have to relate the thrust and the speed with the synchronous speed. That's the same that of the conventional induction motor type. And you can see here for a short primary LIM, you will be getting a curve like this. For the conventional type induction motor, you will get a curve like the same as that of this one. Next, we are moving on to the circuit of the induction motor. You are having, as you know, in the case of a induction motor, you are having a stator. Stator will be having a stator resistance and leakage reactance, and you are having an exciting circuit that is R0 and X0. That is the no load exciting circuit. And here you are having the secondary will be there. That will be having a resistance and leakage reactance. And here induced EMF will be SU2. What you have to do is you have to divide this by S shift factor. You get the parameter. But you have to refer to the primary side or refer to the second side. Here we are referring to the primary side. So you'll be getting R1 X1, R2 dash X2 dash, and you will be getting one more parameter. And right here you will get R2 by S. And R2 by S, if you are adding and subtracting with R2, you will get the two factor R2 dash and R2 dash into 1 minus S by S. This is fictitious representation. And here you will be getting two power will be there. One is depending upon R2 by S, and another one is you can see R2 by S, and another one is you will be having R2 dash into 1 minus S by S. So next one is the various effects in linear induction motor, that is a transverse edge effect, end effect, and gap effect. That's the most important one that will be contributing to the transverse edge effect, and the end effect are contributing to the losses in it. I can take that as equal to the power stored will be equal to half Li square, and the input power that can E will be equal to N into d phi by dt, that is d by dt of N into phi. N into phi is nothing but the reluctance into current L into I. You have to rearrange the expression to get the torque, the reluctance torque. You will be getting half I square into dl by d theta. But in the here, if you are exciting the primary winding, you will get a linear force instead of a reluctance torque, and we can have the expression as same as that of the conventional type, half I square dlx by dx. And this is the inductance profile and force generation in linear synchronous reluctance motor. And here you are having, as you can see, the reluctance, this is the reluctance path. So you will be having the inductance will be minimum to the maximum level, and you will be having the current and the thrust developed. And this will be corresponding to, if it is a positive one, you will be getting a motoring operation. And in the negative part, you will be getting a regenerative operation. As you can see, the inductance profile, the same as that of the conventional switch reluctance motor. You are having half into L into d theta by d, half into I square into dl by d theta. In the case of conventional, here half into I square into dl by dx, since it is having a linear displacement. And in the transverse magnetic flux path configuration, you can see this will be having the moving direction. So you will be having this was the switching positions are provided. And if you are having the inductance, the maximum inductance or the minimum reluctance position, the thrust will be developed, and you can have the action. So in the double-sided linear switch reluctance motor, you are having a stator, and here also you are having stator, and this is the translator part or the secondary part. And here you are having, as you can see, this is the stator, and this is the stator part, and you are having the translator part. This is also possible. And in linear reluctance motor, that is nothing but it's a linear electric motor in which the translational force production occurs by the tendency of the moving part to move towards the separate stationary point where the inductance of the excited winding is maximized. Once the inductance of the excited winding is maximized, means it is in the aligned position, you will be getting the minimum reluctance and the maximum inductance, and the switching operation will causes the continuous linear motion possible. As you can see, the difference between a switch reluctance motor and a linear switch reluctance motor. And in the switch reluctance motor, the efficiency is low, but here the efficiency is high, and it is in mainly low acceleration, but it is high acceleration, power density low, power density high. And the motor that develops torque to turn the shaft are the SRM, here the reluctance torque, and here you are having the thrust, okay, linear thrust. And the more power switches is required, here only unidirectional current flow is or quadrant operation is possible. And the earth fault in one phase will affect, here do not affect. Okay, so these are the references. And thank you. Any questions? Hello.
Yes, ma'am. We'll start taking the questions.
Okay, fine.
So, ma'am, first question is from Bibin Sam Verghese, and he's asking, where is this linear induction motor used in daily life generally?
Okay, the linear induction motor, mainly we can have the power motors, the energy motors, and force motors. Okay, the power motor means in transportation systems, and you can use in traction, trains, conveyors, and which will be having high power efficiency. Clear? And in the energy motor, if it is linear motor, is energy motor, it can be used in aircraft or missile launchers, and which needs high energy efficiency. And it can be used as force motors, where you can have the door closure, or you can have the metal for impact, metal forming, or stop valves you can use here. And in that case, high force to input power ratio has to be maintained. So in various applications are there for the linear induction motor, linear motor.
Okay, ma'am. We are getting more questions. So the next question is from Rima P, and she's asking which type of linear motor is widely used and why.
So linear induction motors are widely used on.
All right. The next question is, can you please explain the difference between thrust and normal force?
Okay, thrust means nothing but that is the useful work done. Okay, that is nothing but the useful work done, or the useful power required to do the work. Okay, that is the thrust one. And the normal force means nothing but you have to align the primary. If the primary is in the off center, that means you have to align the primary into the center part. So you will be having two ejection force, realign force and the ejection force will be there. So this depending upon the resultant force, that force will maintain the primary in the center of the part. Okay.
Okay, ma'am. So the next question is from Averil Ignatius. And, the question is, what is the synchronous speed of LSM? How do we calculate it? Is the magnetic field synchronously rotating?
Okay. So in the case of synchronous speed, in the case of conventional induction motor, you are having the synchronous speed that is nothing but 120 F by P, right? F is the frequency and P is the number of volts. But that is the rotary part. But in the case of linear induction motor, a linear motion, so you are it will be mainly depend on the tau and the F parameter. So pole pitch, that is the distance between the poles, and F is the. So instead of this 120 F by P, you can have this 2 tau F. Okay, Nish.
Ma'am. Hello.
Okay, Nish.
Okay, ma'am. So can I move on to the next question?
Yes, of course.
Okay, ma'am. So the next question is, which is more advantageous, LSM or LRM?
So LSM is there. LSM can be, so many applications are there, and LRM means linear reluctance motor and linear synchronous motor. Normally, we are having linear synchronous motors. Linear synchronous motors are used.
Okay, ma'am. So the next question is from Achudan, and he's asking, can we use for vertical lifts or open escalators instead of synchronous motors? Since what to size ratio is, weight to size ratio is small. That's his question.
Okay. So of course we can use it. So here we are having, you are using the linear motor as a force motor. The force motor means high force at rest and low speed will be during the short interval. Okay. So that means providing thrust. So you are having a high force to input power ratio should be there if you are using for such type of application.
Next question, are there any methods to overcome power loss?
Yes, the end effect means you can reduce the power loss by increasing the poles, but it may have certain limitations. You cannot simply increase the number of poles. That is not a good practice. So you can, that means you can arrange the windings, or you can have the design. That is, specific design can be chosen to eliminate the losses associated with the linear induction motor, such as the end effect and the transverse edge effect.
Next question from Midun, and he's asking how to control speed of linear induction motors.
Speed of a linear induction motor is, so you can have the pole changing method is possible. Pole changing method means you can have suitable stator windings. As I told you, you can have the different stator arrangements possible to vary the speed of the linear induction motor, the same as that of the pole changing induction motor in the conventional type. In the conventional pole changing induction motor, we are having a stator winding. The stator winding can be suitably connected to form the different pole type. So the same manner you can use it here also. And instead of that one, the speed control techniques, you can use inverters also. So inverters means you can have this chopper fed current inverter can be used, or different AC fed converter systems can be used to control the speed. You will be having the thrust as the thrust and the speed as the input, and you can have the inverter. Then you can have a switching sequence will be there. Then you can connect the linear induction motor, and you can take the speed corresponding to that one. You can fed it back, and you can control as a closed loop, and then you can control the speed of the motor. Okay.
Next question is from Karthik. What is the main difference between linear synchronous motor and
the linear synchronous motor and linear reluctance motor means linear synchronous motor is nothing but you are having a conventional synchronous motor. If you are stretch it out, you will be having both the stator and the rotor, or the primary and the secondary are locked together, and you will be having a linear synchronous speed. Okay, in the case of a conventional synchronous motor also, you will be having both will be having rotating at the same synchronous speed, but it is in the rotatory manner. But here you are having a linear manner, but it will be having a linear synchronous speed. Both will be having. But in the linear induction motor, this either primary or the secondary, depending upon the movement, this will be always catching to the synchronous speed, or it will be slip back from the synchronism. That is the linear induction motor. But in the case of reluctance motor, the main thing is you are having the stator is there, that will be energized, and the rotor means that has to be aligned with the stator magnetic field, means you will be getting the minimum reluctance position, or you will be getting the maximum inductance possible. Once you are aligned means you will be getting the maximum inductance level, and you can have a catch up with this one, as in the case of a conventional reluctance motor. In the conventional reluctance motor, you are having a stator and you are having a rotor. The stator will be having either a 8-pole and rotor will be having a 6-pole. If it is having an 8-pole means you can have a 4-phase winding, and if it is having and 6-pole means that means when the stator pole and the rotor poles align means you will be having the maximum inductance level, and you will be getting a minimum reluctance position, and then you will be having the higher inductance level means you will be getting a motoring operation. And when it is in the decreasing level, and once it attains the maximum inductance means it will be remains at a constant for a particular level, and then it will be having a start decreasing level. So when it is start decreasing means you will be getting the generating operation. That is the case with a conventional reluctance motor. But in the case of a linear reluctance motor, the same thing is applicable here also. What you have to do is you have to stretch it out, and you can have different power converter circuits can be used to switch the operation. And if you are switching the operation means you will be getting the maximum reluctance position, or the aligned position will be there with the minimum reluctance, and thus you can attain the thrust or the force. But in the case of conventional reluctance motor, you will be getting it as the reluctance torque. Here only difference is you will be getting it as the linear force or the propulsion force will be obtained. Okay. Okay, Nish. Okay, any more questions?
Yes, ma'am.
Okay.
Next question from Bibin. He is asking, what is the expression to derive linear force?
Expression. Okay, fine. Expression means what you have to get is you have to get the power developed. Power developed will be equal to 3 times, since it is a 3-phase one, 3 times VI cos phi. Is it clear? So 3 times VI cos phi means E means nothing but we can equate to V, so that the applied voltage and the induced EMF will be same. So we can have, since we are neglecting the magnetic losses, and this E induced EMF will be equal to 4.44. F is the frequency, then flux is phi is the flux per pole, and you will be having the number of turns per phase. So 4.44 F phi max into T phase will be the induced EMF level. So if the induced EMF, that means the induced EMF, you are getting it as E1, and that E1 you have to substitute in the power equation, and again you have to substitute from the specific magnetic loading and the specific electric loading, and the specific magnetic loading is nothing but that is the total flux around the air gap divided by the area. So you are getting one equation, that is 3 into 2 T phase into 5 divided by I divided by this L into W. So you will be getting that specific, you have to obtain the average flux density, specific magnetic loading, and you have to obtain the specific electric loading, and then you have to equate the expression and substitute the expression in the average power equation, and then you can obtain the thrust equation is nothing but efficiency into the power input divided by the Vs, or you can have the efficiency into the power, that is the mechanical power developed divided by the rotor speed. The rotor speed is nothing but Vs into 1 minus S, and the mechanical power is nothing but Pg into 1 minus S, that is the same as efficiency into Pg by Vs. So if you are substituting in the power developed equation that we have obtained from the input power and the specific magnetic loading and the specific electric loading, you can substitute here and you will get the final expression in 1.11 into AC into B average, etc. equation. Okay. Okay.
We've got few more questions, and I think we have enough time to ask all those questions as well. So I'll go with the next question. It's asked by Achudan. He's asking, can we use this method to make a pump for conducting liquid, considering conducting liquid as a rotor and exposing to a moving magnetic field? I think the question is
definitely, of course, it's wrong, but he's I think he's asking this one. No problem. Yes, of course we can have, but the thing is this one. Don't know whether he's oh, one more that question. Can you please, is it related with the hydraulic actuators?
The question is actually not clear. I think he's asking, can we use this method to I think it's make a pump for conducting liquids. I think I'll move on to the next question because it's not clear. Achudan, if you could post it again, it would be really helpful to all of us. So without typos and just post the actual question. So ma'am, I'll move on to the next question. Karthik is asking, is the speed...
Anish, wait.
Okay.
Well, maybe he's asking like this, pumping of liquid metal. That is the, right? So I think so.
Yeah.
I think so. He is asking about the pumping of liquid metal. Of course, you can use a small linear motors can be used in pumping of liquid metal. That may be his question. I don't know. I think so. Okay. Okay, Anish, move on to the next question.
Okay. So the next question is speed control of LRM easier compared to LSM? Karthik is asking.
No, speed control of LSM is easier when comparing with speed control of LRM. So the speed control, as you know, you are having the different power converter switches will be there, and you have to fed it back. And then in the case of mainly the ripples will be there. In the case of conventional switch reluctance motor also, the main problem associated with that one will be the torque ripple will be more. Here also the ripples produced in the thrust will be more in the case of switch reluctance motor when comparing with the linear synchronous motor. So linear synchronous motor will be having better. Okay, Anish. Anish?
Aravind, he's asking, what is specific magnetic loading?
Oh, specific magnetic loading is nothing but you are having a total magnetic loading will be there. The total magnetic loading means that is the total flux around the armature periphery at the air gap. So that is the total magnetic loading, and from that you will get the specific magnetic loading, that is nothing but the average flux density over the air gap of a machine. So the average flux density is nothing but that is the total flux around the air gap divided by the area of the flux of the air gap. In the case of conventional induction motor, you are having the number of poles into flux per pole, you will be getting it as the total flux, and you are getting the area of the flux factor of air gap in the induction motor as pi dl. Or you can write that is equal to flux divided by the pole pitch into L. You will be getting in the case of a conventional induction motor. But here you are having the average flux density expression. Okay, so the average flux density expression, as I have explained here, this one, that is P phi m divided by LW. Okay. Anish, is there any question?
Yeah, ma'am. Last question. I think just one more thing, ma'am. Guys, please keep sending your questions. I think we have about like 5-10 minutes left, so you can ask the questions in the Q&A section. And ma'am, I've got one more question. It's asked by Mahesh. He's asking, what is goodness factor?
So goodness factor is the capability of the machine to convert the air gap power between the secondary and the primary. So if you are having the resistivity as rho and mu as the permeability and d is the thickness of the secondary and Lg is the air gap length, and you are having the linear velocity as Vs and the frequency as 2 pi f, then you can have the relation goodness factor that is mainly associated with the non-conventional machines, and that will be equal to mu 0 by rho into d by Lg into Vs square divided by omega, that is 2 pi f. So you'll be getting the goodness factor will be always associated with the non-conventional machines, and it will be mainly the capability of the machine to convert the air gap power between the primary and the secondary. Okay, fine. More question?
Okay, ma'am. That's all the questions we have received as of now. Guys,
okay, fine.
If you have any more questions, please send it, because we have like 5 minutes left. So please send it and I'll ask the questions to ma'am.
Any more questions?
Ma'am, I've got a compliment for you. It's saying it's from Achudan. He's saying your presentation was very informative and excellent. And he's saying liquid, metal, liquid only. So I think he was referring to the previous answer you had mentioned. He asked a question which was not clear, but you answered it correctly by going to the slide. So I think he's thanking you for that.
Okay, fine. Thank you. Any more questions?
I think, yeah, one more again. Another compliment. Nice presentation from Bibin again. Okay, so I think that's it, ma'am.
Thank you. Thank you all. Thank you all.
Or
any more questions?
Nothing as of now, ma'am. So I'd like to thank you